Good morning, everyone. Today we're going to do Unit 6, Lesson 2, Vector Components. So we're going to continue exploring the different characteristics of vectors and continue talking about that idea of magnitude and direction when we're talking about vectors. So yesterday we looked at the difference between a scalar quantity and a vector quantity, and we're going to continue talking about that. So what is displacement versus distance? Well, distance is simply just the magnitude, like we talked about yesterday. So it's the total length of the path that the object traveled. So if we look at the examples that are given here, we can see that this first example shows a distance of just 5 meters, right? And this example below that has a total distance of 8 meters because we go 5 meters in one direction and then 3 more meters in another direction. But again, the direction doesn't matter right now because we're just talking about magnitude. When we start talking about displacement, which is the word we're going to use lots when we're relating to vectors, that displacement discusses the magnitude and the direction. So the displacement is the shortest length between an object's start and end point, as well as the direction of the motion. So again, shortest length tells us that that's the magnitude, and then as well as the direction that it's traveling, that's our direction. So displacement, just like a vector, is your length, your magnitude, and your direction. So if we look at these examples, we're going 5 meters, but it also gives us a direction, right? 5 meters to the right. If we wanted to look at our displacement, in this case our displacement is 2, right? Because we can look at the total distance where we went 2 meters, or we went 5 meters and then 3 meters back. But really from our start to our end, we traveled 2 meters. We might have had to kind of go back and forth to get there, but the distance between the start and the end is only 2 meters. So we're going to look at some examples. This is pretty self-explanatory, but if we wanted to look at what's the distance traveled from A to B in terms of square units, we can see that we go 1, 2, and then down 3, 4, 5, and then over 6, 7. So we would say that the distance is 7, but that's just a magnitude, doesn't give us a direction. If we wanted to talk about the displacement, that's the shortest distance from the start of one point to the other point. So our displacement from A to B, we're going to go 1, 2, 3, and we need a direction for it. So we're actually going 3 down. Go ahead and pause the video and work through the other examples here. All right, there's the solutions to the other one. As we move from one point to the other, the shortest distance between those is our displacement, as well as providing a direction to go from one to the other. Okay, so we'll continue on with the note. So how do we determine the displacement when we're talking about vectors? So remember, the displacement is always going to be your magnitude and your direction. So we're going to think of a vector in terms of its vertical and horizontal components. All right, and when we do that, that's going to kind of help us use some of our previous mathematical knowledge to figure out what's the displacement of a vector, and I'll show you what I mean by that. So if we look at this first vector here, if I wanted to break this vector down into its horizontal, right, so let's say this was our point A, we traveled so far over here, and then we traveled up to here to get to, let's say, point B, right? Similar to those charts before where we moved in certain directions to ultimately get to a point, and the shortest distance between those 2 points is what is going to be our vector. Okay, so along the horizontal there, just like think about if we were on a Cartesian plane or an X and Y plane, this would represent our X vector, because our horizontal is always our X. And this would represent our Y vector. Oops. Okay, and what we've created there is a perpendicular relationship. So you might see them talk about breaking it down to its perpendicular components, and that is what they're talking about. You might also be asked to break down the vertical and horizontal to its rectangular vector components, but the idea is the same. So I could draw a horizontal like this to determine what's the horizontal distance traveled from one side of the vector to the other, right? That would be my x vector. And then if I wanted to make a rectangle out of it, I could put my vertical distance at the start point of that vector as well. And this would still be my y vector. And then we can just kind of, if we wanted to, we could translate that horizontal piece up here or translate our vertical component over there. So you can see I've created a rectangle. So sometimes it might be represented as the rectangular vector components. You can see that it really means the same thing. It's just two different ways of looking at the same idea, right? Breaking down our vector in terms of its horizontal and vertical component. So we're going to take a look at some things we can use based on that. Recognize here that in my first example, right, when we're talking about our perpendicular, we've created a triangle. Well, we know how to find some side lengths of a triangle, right? So this vector here, it's what we call our resultant. It's the result of two other vectors, so I'm just going to label it. The vector v is our resultant. All right, and it can be represented as a direct line segment with magnitude and direction, right? Our vectors are always represented with magnitude and direction. We can use trigonometric ratios because we've created this triangle now, and a right triangle at that. So we can use trigonometric ratios and the idea of Pythagorean theorem to determine the magnitude and the direction of the vectors. And I'll show you what I mean by that. But you should think of direction, we're talking about some type of angle, right? So we know how to use trig ratios to find our angles. And our magnitude is going to represent one of the side lengths of that triangle. Well, that's exactly what we use those trig ratios for, is for finding the side length or the angle of a triangle. So let's break down this vector one more time into its horizontal. And I'm going to make a right triangle since we're dealing with our trig ratios. So our horizontal is x, and our vertical is y. And we should put some arrows on those vectors because, as we know, they do represent a magnitude and a direction. So if we were trying to find or represent theta, we're going to say that that is theta. And notice, especially if we're trying to break this down into our horizontal and our vertical components, that theta is always made with the horizontal. Okay, if we're trying to break it down into its horizontal and vertical components, then we're always looking at theta in terms of the angle made with the resultant and the horizontal. So for the sine of theta, we can look at our triangle and use our vector variables here to identify what the sine of theta would be. So the sine of theta, remember, is going to be O over H. Well, our opposite side here is y. Okay. And over our hypotenuse, which is v. Okay. So if we wanted to rewrite this in terms of y, if we were trying to identify, okay, what is the vertical component of my resultant vector v, then we could simply multiply the resultant over to the other side. So you would get y, the absolute value of y, is equal to v times the sine of theta. Okay, we could do the same thing for our cosine. Think about cosine is our adjacent side over our hypotenuse. Well, our adjacent side is that x vector over our hypotenuse, which is that resultant or v vector. Let's write that again. So if I wanted to rearrange that for x this time, then I would just multiply the vector v or our resultant over to the other side. So the x vector would be equal to the resultant times the cosine of theta. And finally, if we were given our x and our y, right, the two legs of our triangle, then we know how to find that third side. So if we're going to say v squared, that's going to be equal to the sum of the squares of the other two sides. So that x squared plus y squared. Okay, so keep those things in mind as we're trying to determine our vertical and our horizontal components. So looking at an example here, so you have a resultant, resolve each vector into its rectangular components. And just remember that our rectangular components are our horizontal and vertical components. So if I look at my first example here, I have a 30-degree angle, and I have some resultant vector here. Right, so we'll say that this is our V. We need to identify what's the horizontal force, what's the vertical force. So what's my X, what's my Y. So I'm going to use these rules we just identified up here. So to find my Y, we're going to do our resultant or our vector, which is 25, times the sine of our theta, which is 30 degrees. So when we do 25 times the sine of 30, we're going to get 12.5 newtons. Okay, if we're trying to identify our x, I'm just going to write that out. I should have. So our x vector is going to be equal to, remember, our resultant, or our v vector, times the cos of theta. So that means x is going to equal 25 times the cos of 30. So x equals 21.6. And I'm just going to come back up here and write our original function for y. So these should be absolute values. Right, so the vector y is equal to our resultant vector times the sine of theta. That's where all that information came from. So we should always have a therefore statement. So therefore, 21.6 newtons along the horizontal and 12.5 newtons along the vertical. Let's set up the next one together, and then we'll pause the video and get you to work through it on your own. So you have another vector here on a Cartesian plane. So we're going to need to break it down again to its horizontal and its vertical components. So I'm going to draw this as more of a triangle. We're going to kind of break it out. So if we're trying to identify this triangle here, well, we have a vector, a resultant vector of 5 degrees. We need to know this theta. Remember, theta is always made with the horizontal. Well, if this is 105, then this must be 15 degrees. So let's just draw that over here. We have a bit more room. So as long as theta is made with that horizontal, we're all good. So 5 meters per second. So go ahead and pause the video and see if you can identify what are the horizontal and vertical components. There's the solutions for that example. So again, we just found our vertical by taking the theta and multiplying it, or sorry, taking our resultant vector and multiplying it by the sine of theta. You get 1.3 meters per second. And then for our horizontal component, we're going to take the resultant vector and multiply it by the cosine of theta. You get 4.8 meters per second. And because this is on a compass, we can identify if the direction is north, east, south, or west. So we are moving 4.8 meters per second in an east direction, and then 1.3 meters per second in a south direction. So let's continue looking at a few word problems, and then we are all set for today. So a train is traveling at 200 kilometers per hour. So let's recognize that this is going to be the magnitude of our vector, right? Because it's some kind of scalar amount. And this is our direction. So remember, our vectors need to have magnitude and direction. So a train is traveling 200 kilometers per hour in a direction of north 55 degrees east. Draw a diagram of the velocity of the vector and its perpendicular components. Remember, those are the same as the rectangular components. It's just our horizontal and vertical component. So if we were to draw this, especially since they gave us a compass direction, we're going to draw it on a compass. So it's north and then moving in an east direction. So we should be somewhere here in quadrant 1. So we have the magnitude is 200 kilometers per hour. All right, and the direction is north 55 degrees east. Remember that those quadrant bearings start from the north or south line and then move in an east or west direction. So this is 55 degrees here. But we need to create our triangle with our horizontal in order to be able to identify that theta. I'm just going to make that a little longer. Right, so my triangle is going to be drawn from the end of my resultant, or the end of my vector, down to the horizontal, so we can create this theta in here. Well, if we have 55 degrees as a quadrant bearing, then we should be able to identify this, right? It's just the difference of 90 to 55. So this will be 35 degrees in here. So the diagram wants us to break down where our horizontal and our vertical components are. So we know that our horizontal is represented with an x vector, and our vertical is represented with a y vector. Okay, so part B says determine the magnitude of the vertical and horizontal components to 1 decimal place. So go ahead and pause the video and work through finding what the magnitude is of the horizontal and the vertical. All right, there's the solution for that. So same idea, multiplying the vector, the resultant vector, by the cosine or sine when you're trying to determine the vertical and horizontal components. And then always wrap it up with a therefore statement. So therefore, the train is traveling 163.8 kilometers per hour east, because that's our horizontal direction, and 114.7 kilometers per hour north, because that represents our vertical component. One more example. Okay, just after takeoff, an airplane was climbing at an angle of 15 degrees from the horizontal and had a speed of 160 miles per hour. So let's just identify again. 15 degrees from the horizontal is going to represent our direction and had a speed of 160 miles per hour. That's our magnitude. Remembering that vector always has to have a direction and a magnitude. So let's draw a diagram and find the speed of the aircraft's shadow on the ground. So when they're saying shadow on the ground, the speed of it, that just means what's the ground speed. Okay, so when we're thinking ground speed, we should be thinking about that horizontal component. But first, let's draw our vector. So we have a vector here. I'm going to try, we have an airplane. Doesn't really look like much of an airplane. It's traveling 160 miles per hour, and it makes an angle with the horizontal, which we'll say is our ground, of 15 degrees. So I'm just going to finish off that triangle there by drawing that vertical component. Okay, so our horizontal component there will be represented with x, and our vertical component could be represented with y. Okay, so we're going to draw a diagram of it and then find the speed of the aircraft shadow on the ground if the sun was directly overhead. So again, we're trying to find that horizontal element, so we're working to find x. So the magnitude of x, or our vector x, is going to be equal to our resultant, which is 160, times the cosine of theta, which in this case is 15. So x is equal to 154.5 miles per hour. And we'll put that into the therefore statement. So therefore, the ground speed is 154.5 miles per hour. Okay, last part here. Calculate the height of the aircraft 2 minutes after takeoff. So when they're asking us to find the height, we should be thinking about that vertical component. So this time we're going to find the vector of y. So we know to calculate our y vector, we're going to take our resultant vector, or that hypotenuse, and multiply it by the sine of our theta, which is 15. So the vertical speed is 41.4 miles per hour. So this represents our vertical speed, but that's not what the question's asking here. We needed this to help us answer the question, but that's not exactly what they want. They want us to know, they want us to calculate the height of the aircraft after 2 minutes. Well, if we have the miles per hour, right? We found this first. We can take that speed, or that miles per hour, and we can now find the height after 2 minutes. Which, think about 2 minutes in terms of hours would be 2 out of 60. So to calculate our height, we just have to take the speed, which is 41.4 times how long we're looking to calculate it for, which is 2/60ths of an hour. So if we multiply that together, our height is going to equal 1.4 miles. So we'll give it a nice therefore statement. So therefore the plane is 1.4 miles high after 2 seconds. That's it for your note for today.